bit about this equilibrium constant. Okay, now that I have spent some time explaining what equilibrium is and how it talks about a reversible reaction that sort of reached a point at which the forward rate and the backward rate are equal, and so the amount of reactants and products is stable. It's not changing anymore. I want to have a way to numerically represent different reactions and where they reach equilibrium. And I'm going to call this a K. It is an equilibrium constant. I abbreviate it with a capital K. And it's a number that's characterizing when the reaction reaches equilibrium. It can be experimentally measured. So essentially, I wait until it's reached equilibrium, and then I measure, well, how many products are there now, and how many reactants are there now, and I can measure it using complicated formulas. But it's not going to change. Once it's been measured for a particular chemical reaction, it is. And we can put it in a table, or I can give it to you in a problem, and there will be information that you'll need to know. And it tells us about the favorability of the reaction and whether we should expect to see mostly products or mostly reactants. In a reaction that reached equilibrium very early on, maybe I have mostly reactants and I have very little products. In a chemical reaction that reached equilibrium after a long time, maybe I have mostly products and just a tiny bit of reactants left unreacted. I can write a formula for it, but that formula is dependent on the chemical reaction. So every time I have a new chemical reaction, I get a new formula. So our first task has to be getting good at writing what we call a K expression. Okay, the K expression, this is this formula that relates to this K number that can be measured. So somewhere I could get this K in a table from some scientist who's measured it. And it's relating to the concentrations of how much product do I have and how much reactant do I have when it's at equilibrium. It only applies to once a reaction has reached equilibrium. If I had a reaction of A and B forming C and D, and the little a, little b, little c, little d are the coefficients of the balanced chemical reaction. The format of this expression is my K is equal to the concentrations of the products raised to their coefficients power divided by the concentration of the reactants raised to the coefficient power. Let's be careful here. So these brackets, if I put a bracket around a chemical formula, A is a chemical. It's water, it's sodium chloride, it's a chemical. When I put it in brackets, it's now referring to the concentration of that chemical. So the molarity of that chemical. So this is now a number of moles per liter of that solution. So this would be we would pronounce this the concentration of C raised to the C power times the concentration of D raised to the D power. And in the denominator, I have the concentration of A, reactant A, raised to its coefficient power, multiplied by the concentration of reactant B, multiplied by its coefficient. There's one trick too. The concentration of a pure solid or liquid is 1. So when we look at a chemical reaction, if any of these have a state of solid or liquid, we can either replace the whole thing to 1, and it doesn't even matter what the coefficient is because 1 raised to any power is still 1. So a lot of times they would just disappear from the K expression because they're not going to change anything. Let's do an example because it's kind of complicated. Every chemical formula I have, every chemical reaction I have has a different K expression. So in this case, I want you to write the K expression for the reaction, that should say K expression, for the reaction 2 hydrogen gas plus oxygen gas makes 2 water gas. I have one product, it's water. I'm going to put it in brackets for concentration. And I'm going to square it because there's a coefficient of 2 in there. Notice the entire chemical formula, H2O, goes inside the bracket. Outside the bracket goes the coefficient, and that would mean I would take the concentration of the steam and I'd square it. On the bottom, I'm going to do my reactants. I have hydrogen is one reactant, hydrogen H2, the full chemical formula goes inside the brackets, and then it's squared because it has a coefficient of 2. I'm going to do the same thing for oxygen, only oxygen has a coefficient of 1. So I put the whole chemical formula of oxygen inside the brackets, the concentration of oxygen, and then I don't raise it to any power because the coefficient is 1. So this would be my K expression for this chemical reaction. So one skill that you really want to be good at is just taking a chemical reaction and being able to write the K expression for it. Once I have a K expression, I can start using it with actual numbers to get more information. Go ahead and stop it.